Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be doing another calorimetry problem involving a reaction and a calorimeter. So let's get into this. So in this problem we have a quantity of 2.00 times 10 to the second milliliters, or 200 milliliters, of a 0.862 molar HCl solution mixed with 2.00 times 10 to the second milliliters, or 200 milliliters, of a 0.445 molar barium hydroxide solution in a constant pressure calorimeter having a heat capacity of 453 joules per degree Celsius. The initial temperature of the HCl and the BaOH2 is the same at 20.48 degrees Celsius. Given that the heat of neutralization for the process, this process here, is negative 56.2 kilojoules, what is the final temperature? Assume that the specific heats of the solutions are the same as water. Okay, so where do we begin? Well, we have a balanced equation here. So this is the equation, this is the net ionic equation. H plus OH minus gives us water. So we have the hydrogen, or in other words, hydronium ion, H3O plus, but we usually write it as H plus the hydroxide ion gives us water. The rest of the ions are just spectator ions, so they don't really participate. They're not part of the reaction, so we can ignore those. That's not important. So this is the reaction that goes on, so that's what we're going to be focused on. So first thing we want to do is we got two amounts of reactants that are being mixed together in our calorimeter. So that reaction is going to produce heat. You see here, it's a negative 56.2 kilojoules. So that's per mole of product formed, right? But we don't know how much product is actually formed because we don't know what the limiting reagent is. So that's the first thing we need to do, is figure out the limiting reagent. How do I know that this is a limiting reagent problem? Anytime they give you a reaction and they give you amounts of both reactions, they don't tell you any other information. They don't tell you that, oh, the one reactant A is going to be used up, or it all reacts to completion or something like that. They don't really give you any information. They just give you, here are the amounts, this and this. A is this, B is this. That's it. In that case, you know it's got to be limiting reagent problem because you don't know what's going to be used up first. So you got to decide that. So I'm going to start with HCl. They gave us 200 milliliters of HCl and the molarity. I can use the molarity as a conversion factor to convert from liters to moles. And then I can use the balanced equation to convert from moles to moles of the H to moles of water. That's one thing I could do, right? And so I can convert both of those and see which one gives me the lesser amount of water. The one that gives me the lesser amount of water is the limiting reagent. And then that amount that is produced from the limiting reagent is the maximum amount that can be produced from this reaction. So let's go ahead and figure that out. So I have 200 mils of HCl, which is where we get the H plus from. So I'm going to calculate the moles of H plus. So if I'm going to do this, step by step clearly, I'm not going to skip any steps so that everyone knows what's going on. So I'm going to take the 200 milliliters. So that's what this is, 200 milliliters of the HCl solution. And of course, I want to use molarity to convert to moles of HCl, but I need to convert this to liters first because molarity is moles over liters. So I have milliliters here, so I'm going to put 1 milliliter on the bottom, and 1 milliliter is 10 to the negative 3 liters, or 1/1000th of a liter, because milli means 1/1000th of. So I'm going to put 10 to the negative 3 liters, and this is HCl solution. So now the milliliters of the HCl solution cancel out. Now I have liters of the HCl solution. And next, now I can use the molarity. So now I know that the molarity is 0.862 moles per liter. So now I can do that. So 1 liter of the HCl solution on the bottom and 0.862 moles of HCl. So liters of the HCl solution cancel out. Now I have moles of HCl. Now I can convert that to moles of H plus because the H plus comes from the HCl, right? It's a 1-to-1 ratio, so I can do that. So I can use the mole ratio in my HCl. So it's going to be 1 mole of HCl gives me 1 mole of H plus. So moles of HCl cancel out. Now I have moles of H plus, but I want moles of water. And look, it's a 1-to-1 ratio in the reaction equation here. So now it's last conversion factor. So on the bottom, we have 1 mole of H plus and 1 mole of H2O. Moles of H plus cancel out. I get my moles of H2O. And so all I need to do is multiply across the top, divide by the bottom. All the bottom are ones, so that's not a big deal. When I calculate that, I get 0.1724. Yeah, 0.1724. So that's the number of moles of H2O. Now, I can do the same thing now with my 200 milliliters of the barium hydroxide. So let's go ahead and do that. So here, again, I'm going to start with 200 milliliters of the barium hydroxide, and this is solution, over 1. I'm going to convert milliliters to liters again because I want to use the molarity. So the molarity is 0.445 molar. So I need to convert this to liters in order to use the molarity as a conversion factor. So again, 1 milliliter of BaOH2 solution on the bottom, and that's going to be 10 to the negative 3 liters of the barium hydroxide solution. So milliliters cancels out. Now I have liters. Now I can use the molarity, 0.445 molar. So it's going to be 1 liter of the barium hydroxide solution on the bottom and 0.445 moles of the barium hydroxide. So now liters of the solution cancel out. Now I have moles. Now I can convert moles of barium hydroxide to moles of the hydroxide ion. Notice that the mole ratio here is the formula. For every one of these, I have 2 hydroxide ions, so the mole ratio is 1 to 2. So 1 mole of barium hydroxide gives me 2 moles of the hydroxide ion. So that's easy to forget. Don't forget that. So down here I'm going to put 1 mole of barium hydroxide. And then here I'm going to put 2 moles of the OH minus. So moles of the barium hydroxide cancel out. Now that I have moles of hydroxide, I can use the balanced equation here. 1 mole of hydroxide gives me 1 mole of water, so it's 1 to 1 again. So 1 mole of hydroxide ion gives me 1 mole of H2O. Moles of the hydroxide ion cancel out. Now I am done. So again, all I need to do is multiply across top, divide by the bottom. All the bottom are 1, so don't need to worry about that. When I calculate that, I get 0.1780. So this is equal to 0.1780 moles of H2O. So notice here that the amount of water produced from the 200 milliliters of the HCl solution gives me 0.1724. That's the maximum amount that I can get from the 200 milliliters of the HCl solution. If I look at the milliliters of the barium hydroxide solution, the maximum amount that I can get from that is 0.1780. So because the hydrochloric acid gives me a maximum of 0.1724, less than this one, this is the max that I can make. What this is telling you is that once I create or produce 0.1724 moles of my water, I have run out of the HCl. Once you run out of one of your reactants, you're done. No more reaction. So this HCl, or the H plus ion, is the limiting reactant. So that means that this is the maximum amount of water that can be formed. So I'm going to write that here. So 0.1724 moles. Okay, now that we know what our limiting reactant is and how much water, the maximum amount of the water that we can form, we can move on to the next part, which is the calorimetry. So I'm just erasing this to give myself some space. Okay, now that we know what the limiting reagent is, the next thing we need to do is figure out what's happening, what's being reacted with, what's absorbing the energy, what's losing or losing the energy. So we have a reaction. We said that this is the amount of kilojoules that's produced from the reaction process, from this neutralization reaction. This is the amount per mole. So if we were to produce 1 mole of water, then this was the amount we would get. But we didn't produce 1 mole of water, we produced this amount. So we need to calculate the delta H for this particular reaction. How much heat was actually released by this reaction. So to do that, we just take the 0.174 724 moles of H2O, and this is going to be the amount of kilojoules per mole of water. So then, since we have moles of water here, we're going to put 1 mole of H2O, and then we got negative 56.2 kilojoules. Moles of water cancel out. Now we have kilojoules. And so now we can figure out the number of kilojoules produced from this amount of moles. And when we calculate that, we get negative 9.689. But let's convert this to joules, and I'll tell you why. So 1 kilojoule of energy is equal to 1,000 joules of energy. Kilojoules cancel out. So if we transform this to joules, then we're going to get, let's see, 9689. So 9689 joules of energy is produced. And that's going to be a negative number because this is negative here. So remember, the negative is important because this is telling us that this is the amount of energy released. So you got to have the negative as part of your calculations. Okay, so where are we? Now we can do the calculation. So I'm going to rewrite this up here, 9689 joules. That's equal to the delta H of this reaction. Okay, so now for the calorimetry. So we have a few heats that are being absorbed and released. So there's heat being released by the reaction, right? So we got a few Q values to worry about. So Q1, Q2, and Q3. So the first one, of course, is going to be the heat of the reaction. So we're going to call that delta H of the reaction, and that's what we just calculated. That's going to be equal to negative 9689 joules. So this is the amount of heat released, but that heat is absorbed by two things: the calorimeter and the solution in which the reaction is taking place. So we got the Q's for that. So the calorimeter, they gave us the specific heat of the calorimeter, and the calorimeter is going to be at the same temperature as the original solutions, because the solutions are going to be mixed in the calorimeter. So the idea here is that the calorimeter and the solutions in the calorimeter are all at the same temperature, right? If the calorimeter was not at the same temperature, then heat would be given or lost by the calorimeter to the solution inside. That would make things a bit more complicated. So the assumption here is that the calorimeter is going to be at the same initial temperature. So if we're going to do the calorimeter, right, so this Q2 we'll call Q of the calorimeter, which is going to be equal to the specific heat or the heat capacity of the calorimeter. And notice here that the units of the specific heat of the calorimeter are joules per degree Celsius. That's why I wanted to convert this to joules so that we can get that same unit and they'll cancel out. And the other thing I want to point out is that, look, it's joules over degrees Celsius. So if I'm thinking about an equation, because remember, this is Q, this is heat, right? Q stands for heat. It represents the heat lost or gained of the substance, in this case, the calorimeter. So the calorimeter is going to be absorbing heat. And so here we need joules. We need a heat energy. And so in order to get that heat unit, that energy unit, joules, we need to get rid of the temperature, the degrees Celsius here. So how are you going to get rid of degrees Celsius if it's on the bottom? You multiply by degrees Celsius. So the equation that we want to use for Q here, in order to get our joules, is going to have to be the specific heat of the calorimeter, right? So we'll say C of the calorimeter multiplied by delta T of the calorimeter, which is going to be the 400, or let me specify this. So the delta T, remember delta T is final temperature minus initial temperature, so we can substitute that in because we need to find the final temperature. That's what they're asking us for. So we should substitute that in for delta T. So we end up getting the specific heat of the calorimeter multiplied by final temperature minus initial temperature of the calorimeter. And so then this is going to be equal to, of course, the specific heat 453. So that's going to be 453 point, oh no, just 453 joules over degrees Celsius multiplied by the final temperature, which is what we got to find, minus the initial temperature, which is what they gave us over here, 20.48 degrees Celsius. So 20.48 degrees Celsius. Okay. So this is going to be our Q1 right here. So this is what we're going to have for equal to Q2. And our final Q is going to be the Q of the solution. So the solution is going to absorb some of that heat from the reaction as well. So this is going to be Q of the solution, which is going to be equal to Q equals MCAT. So the mass of the solution multiplied by the specific heat of the solution multiplied by delta T of the solution. So the mass of the solution is, they gave us the liters here, right? So they gave us milliliters, right? So we have milliliters of solution here mixed in with milliliters here. So we have 200 milliliters of one solution, 200 milliliters of another solution. They're added together, right? So the solution is now have 400 milliliters. And the thing here, notice that we're asked to assume the specific heats of the solution are the same as water. Because of that, it's safe to assume that the density is going to be the same as water. So we know if the density of water is 1 milliliter per 1 gram, or sorry, the other way around, 1 gram per 1 milliliter, that means that the number of milliliters is equal to the number of grams. So the mass of the solution is the same as the total mass the mass of the solution is the same as the milliliters of the solution, the volume of the solution. So then the mass here is going to be 400 grams. It's 400 milliliters, therefore 400 grams. So we're going to have 400 grams for the solution. That's going to be multiplied by the specific heat. We are told that the specific heats of the solutions is going to be the same as water, and water is 4.18. So 4.18 joules per gram degrees Celsius. And again, multiplied by the temperature change. So it's going to be final temperature minus the initial temperature, which is again 20.48 degrees Celsius. So now that I have that, I'm going to set up the equation. Remember, the equation is going to be 0 equal to the 3 Q values. So Q1 plus Q2 plus Q3. And then we just substitute in for these what we just found. So this is going to be delta H of the reaction, right? So if I put this in, so this will be delta H of the reaction plus Q2, which is going to be this right here. Right? The specific heat of the calorimeter multiplied by final temperature minus initial temperature of the calorimeter. Right? So Q2 is this. And then we're going to add to that Q3, which is the Q of the solution, which is this here. So it's going to be the mass of the solution times the specific heat of the solution times the delta T, which is, again, final temperature minus initial temperature. So that's everything added together, and it's all equal to 0 because, remember, the heat that's released from one substance or thing is going to be completely absorbed by the other substances or things that are in the air as part of the calorimetry problem, right? So in this case, we have three things involved. So we have the reaction releasing the heat, and then we have the calorimeter and the solution absorbing the heat. And so we're assuming no heat is lost. It's completely transferred, and so therefore it's going to be 0 is going to be the result. So all three of these should add up to 0. Okay, and then basically this, I'm just going to take these and plug them in. So then this is the heat of the reaction, which is, where did it go? Negative 9689. So this is going to be equal to negative, 9689 joules. And then this, I'm going to plug in the value. So here it is with the values plugged in. So that's going to be plus, where is it? Oh, this here. So 453 joules per degree Celsius multiplied by the temperature change, which is, oops, sorry about that. So final temperature minus 20.48 degrees Celsius. And then I'm going to add this, but I plug these into this here. So that's going to be plus 400 grams multiplied by the specific heat of water, 4.18 joules per gram degrees Celsius, multiplied by the temperature change, which is, again, TF minus 20.48 degrees Celsius. And so now all I need to do is simplify and solve for TF. So let's go over and do that. So now the rest of this I don't really need anymore, so I'm going to erase so I can continue up on top here. So this I don't need anymore. Okay, so I've got this here. Let me double check. Yep. So now I'm going to, so 0, oops, I don't want, that's a little too high. I don't want to run into anything. So 0 is going to be equal to negative 9689 joules. Now what I need to do is I need to multiply this to both of these. So when I multiply this to this, I'm going to get added a positive 453 joules per degree Celsius multiplied by the final temperature, whatever that is. We're going to solve for that. And then these two multiplied together. And when I get that, let me see, that's going to be 92.77.4. 92.77.4. So negative 92.77.4. And since I multiplied these two together with this, the degrees Celsius are going to cancel out, and I'm going to end up with joules here. So do you see that? So if I multiply this, I'm multiplying the units. So this times this, the degrees Celsius are going to cancel out. And I'm going to be left with joules. So that's what I got here. And then I do the same thing here. So I've got this here. When I multiply those together, let's see here. Yeah. So I'm going to multiply these two together. And then this, whatever the result of this is going to be multiplied to these two here. So these two multiplied together, multiplied by this, gives me a positive value, and that's going to give me 1674.4. So that's 1674.4, and that's going to be multiplied by joule. So here again, so in this case here, the grams cancel out. So I'm left with joules over degrees Celsius again. So then I'm going to have joules over degrees Celsius, and then that's going to be multiplied by TF. And then again, I'm going to multiply these two together and then multiply by the negative 20. So that's going to give me a negative there. And when I do that, I get, what do I get? Negative 34,291.7. 34,291.7. Let me double check that. 34,291.7 joules. Okay, that is correct. Joules. Okay, so now I have it a little bit more simplified. So now what I want to do is add the like terms together, right? So here I have a TF term. Here I have a TF term. So I'm going to add those together. So when I add these together, notice they have the same units, so they can be added together. When I add those two together, I get let's see, 2127.4. So 0 is equal to 20, what did I say, 21? Yeah, 2127.4. 2127.4. And it's again joules per degree Celsius multiplied by TF. And then I'm going to add the joules together. They have like units, like terms. So this is joules plus this is joules plus this is joules. So I have 1, 2, 3 terms with joules. When I add that together, it looks like I'm going to have negative 53,000. So they're all negative. So it's going to be negative 53,258.11. 258.11 joules. Okay, now this is much simplified. So now all I need to do is get this over here to this side. So I'm going to get this over here. So I'm going to add 53,258.11 joules. And I'm going to add it over on this side with the 0. So I'm going to add 53,258.11 joules. So now I'm going to end up with 53,258.11 joules is equal to 2,127.4 joules per degree Celsius multiplied by TF. Now, to get TF, all I have to do is divide both sides by 2127.4 joules per degree Celsius. So I'm going to do that. So let me make this clearer. So divide this by 2127.4 joules per degree Celsius. Divide this by 2127.4 joules degrees Celsius over degrees Celsius. So this is going to cancel out, leaving me with TF. And TF, the final temperature, is going to be equal to this divided by this. But notice when I divide these, joules cancel out, and I'm left with degrees Celsius. So when I calculate this, my final temperature is 25. So final temperature is equal to 25.03 degrees Celsius. And that, ladies and gentlemen, is how you do this kind of problem. I hope you enjoyed this video. If this video helped you out a lot, if you learned anything from this video, if you enjoyed this video at all, please like the video, share the video, hit that like button over here somewhere. Also, do me a favor, subscribe to my channel, help me out here. Hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or problem you need help with, or if you have a topic you want me to cover, put that down below. I would like to do that for you. Thanks for joining me, and have a great day.